Hello there. Let's talk about binary search tree terminology. If you saw my previous video, we talked about how to define a binary search tree, meaning a whole bunch of rules so that if the thing you're looking at follows all the rules, then you know you're actually looking at a binary search tree. If not, then not. So see my previous video if you want to know for sure whether you're looking at a binary search tree. For now, we're just going to talk about some associated terminology. Okay, so the first thing we should probably obviously talk about is the root node over here. So in my previous video, we talked about nodes, right? So this is kind of a graph with a whole bunch of rules on top of it. That means we have nodes and edges. So if you look at the very top node here, sometimes also referred to as a vertex. I think in binary search tree terminology, we usually say nodes. I can't actually remember. But so look at the 42 there. That node is the root node of all other nodes. It's the highest common ancestor in the entire tree. So this is the root node. First bit of terminology. Also, I tried to sneak past you ancestor. So these trees are supposed to be written in a way that kind of looks like they have a family hierarchy with one parent per child, like not two children per parent, but just like one parent and then either 0 or 1 or 2 children. So we'll say that ancestors are higher on the tree. So that means 42 is actually an ancestor of 33, and it's also an ancestor of 12. It's also an ancestor of 19. Just anything that's higher is an ancestor of anything that's lower. We could also say that 33 is an ancestor of 39, and 12, and 19, and so forth. You can probably also imagine that we have children and grandchildren. Yeah, we do go that far in binary search trees. So the 42 node, it has 2 children. It has a left child and a right child. The 33 is the left child. I'll put LC for left child. And the 67 is its right child. I'll put a RC there. The 67 in turn has 2 children. The 56 has no children of its own. So sad. The 33 has 2 children. The 12 only has 1 child. It was, playing it safe, I guess. You never know if these children are going to come out and just like run amok and engage in constant shenanigans. So the 12 has a right child, but no left child. That's okay. In terms of going higher on the tree, anything that is higher is an ancestor. Sorry, I should have said lower. Anything that's higher is an ancestor. Anything that's lower is a descendant. So if we're looking at the 33 node, the 33 is a descendant of 42 because it's the left child of 42. It's also an ancestor of anything that comes below it. So it's an ancestor of 12 and 39 and 19, right? So if we're looking at 33, we've got a left child over here and we've got a right child over here. And then we have a grandchild, which is the 19 node. We don't really have left and right grandchildren. You could say a grandchild in the left subtree or the right subtree. Talk about subtrees in a second. The 33 has a parent node, which is just the 42 node, which is also the root node, of course. It's got a sibling. The 67 is the sibling. You can tell something's a sibling because it's got the same parent as you. It's the people that you're usually fighting with, right? Anyway, so if we're looking at any node in particular, it might have a whole bunch of ancestors above the tree. It might have a whole bunch of descendants below the tree. It has siblings, or it usually has 0 or 1 sibling because in a binary search tree, we can only have up to 2 children per node. It's got sometimes, grandparents and great-grandparents and children and great-grandchildren. So just think about the hierarchy like a family tree would have. Okay, moving on to some more terminology. Next thing is we have internal nodes and also external nodes. So what do I mean by internal? Internal means a node has more than 0 children. It has 1 or 2 children. So I'm going to put internal on the 33 because the 33 node has children. The 12 also has children, so it's internal. The 39 does not have children, so it's not internal. 67 has children, so it's internal. And the root node 42 also has children, so it's considered internal. That 42 has a lot of different names. It's the root node, it's the greatest common ancestor, it's an internal node, and so forth. Notice how the other nodes that I have not highlighted, they have 0 children. So when a node has 0 children, it's known as an external node. It's also known as a leaf. because we're talking about trees. And I guess it's kind of like a nice synonym. So the 19, the node with no children of its own, is a leaf. So is the 39. So is the 56. So is the 76. I just want to point out also, if you were with me on my last video, then the numbers need to be ordered from left to right. But don't worry, we're going to do another video where we build a complete tree from scratch. There's some more terminology we should talk about. So I'm going to get rid of all these externals and internals real fast, or the labels. We should talk about the left subtree versus the right subtree. I mean, what is a subtree anyway? The subtree is basically, a subtree is basically just pick any node you want in the entire tree. Let's pick the 76, and then we'll just pretend that it's the root node of a separate tree starting with 76. So if there was anything below it, then all those nodes would be included. So this 76 right here, it really has nothing underneath it. It's a leaf, which means, well, it can be the root node of its own subtree, but the subtree is just going to be a tree of one node. So kind of boring, right? Yeah, boring. If instead we decided to look at the 33, which is a little bit more interesting, and we called the 33 the root node of its own subtree, then really what we're saying is all these nodes here are included in that subtree. So if I told you, give me the subtree starting with node 33, then you would say, oh, it's 33, 12, 39, 19. All of the nodes that are descendants of the subtree root node that we picked out. So subtree just means, you know, like a little fragment or a portion of the original tree. You could also say that the entire tree is a subtree of itself if you chose the subtree root to be the real root node. I mean, that's not super useful, but you can do it. Anyway, so if we decide to say that the 67 is the root of its own subtree, then, well, same thing, right? Any node starting with 67 and below in terms of descendancy is going to be considered part of the subtree. I've highlighted the left subtree and the right subtree of the root node because that's usually what we say. We'll say this is the left subtree over here, and then over here we're going to say this is the right subtree. Meaning, if you look at any node at all, if it has a left child, then that left child is the root node of the left subtree of the node in question. Same thing for the right. So if I say, all right, let me duplicate this real fast. Let me get rid of actually this real fast too. If I say, okay, give me the left subtree of the 33 node, well, then you would know to include the 12 and the 19 because the left subtree of the 30 node has to, the 33 node has to start with the left child of the 33 node, which would be the 12. And we'll just say, okay, the 12 is now the root node of its own subtree, and then anything that goes below it in descendancy is going to be considered part of that subtree. So that highlighted subtree is the left subtree of the 33 node. The 39 is the right subtree of the 33 node. I think I just did the wrong color. Let me do that in gray. Right, so we can do left subtree and right subtree for any node in the entire tree. I mean, if a node has no children, then there are no subtrees, but we can still look and check. And if there are children, then we've got subtrees, or left and right subtrees. Okay, so now that we're done talking about subtrees real fast, let's talk about the depth of a node. So for me, I like to say that the depth of the root node is 0. And so I'll just, I guess we could start off by putting a 0 on the 42, indicating it has 0 depth. Imagine maybe it's a buoy in the water and it's just like sitting, floating like directly on the water. So it has no depth. It's just like kind of on the surface. But if you draw your binary search trees in this nice, pretty way, where every single time you go down a generation from parent to child, you maintain, I guess, like the same y coordinate for same leveled nodes, then it's really easy to calculate the depth of every single node. Let me show you what I mean real fast. If you saw my video previously, then you already know this, but the 42, it's got 2 children. So if I go down to get one of its children, I'm going down to the 33, and then I'm going down to the 67, right? Since those 2 children are on the same, I guess, level as if we were looking at a family tree, they should be physically on the same level. They should be on the same y coordinate, or the same horizontal plane. If we go down one more level, which means any child of 33 or any child of 67, then those all should be lined up also. So notice how these are all lined up on the same y coordinate. Then if we go down another level, then this 19 here is just kind of by itself because the tree is not very big. So if we draw the tree like this, which is a really smart way because it's easier to debug, like whether it's a valid binary search tree and all sorts of other things, then we can easily write down the depth kind of on the side of the graph. We can say, all right, here's depth 0, and here's depth 1, and here's depth 2, and here's depth 3. Just every time you go down one level, you just increase the depth. And now you know the depths of all the nodes in the entire tree pretty quickly. The 19, I'm just going to maybe do this in red. The 19's got a 3. The 12, the 39, the 56, and the 76 have a depth of 2. The 33 has a depth of 1. And the 42 has a depth of 0. So all these nodes in the tree have their own depth, which are very easy to calculate if you draw the tree well. The next thing after depth is the height of the tree. So what is the height of the tree? Well, that's basically the depth of the deepest node plus 1. Or if you try to find a path to the very deepest node, what is the minimum number of nodes that you must touch when you start at the root node and then find your way to the deepest possible node in the entire tree? So if you notice, the 19 node is definitely the deepest node in the entire tree. It's got a depth of 3, which means the height of the entire tree is 4. Height equals 4. And maybe I'll change that to like just black or something. Okay. So again, let's do it the other way real fast. If we're kind of just walking down the tree, let's start at the 42. And then we go down to the 33. We've touched 2 nodes so far. We go down to the 12. We've touched 3 nodes. We go down to the 19. We've touched 4 nodes. So the height of the tree is 4, or the number of nodes that you need to touch as you make your way down towards the deepest node. Or just a shortcut is the deepest node's depth plus 1. And that's the height of the tree. You can also have a height of a left subtree and a height of a right subtree. So let me just, what's going on here? I think my thing is crashing. Hello? Oh. I was definitely crashing. I think my CPU is burning right now. All right. I'm going to be complaining about my new CPU for a long time. I sprung only a few bucks for the best CPU that this motherboard could hold, but it's an old motherboard. So my upgrade was about 30-something%. I'm eventually going to have to like build a brand new computer. Anyway, so suppose we're looking at the 67 node, and the question is, what is the height of the left subtree of the 67 node versus the right subtree of the 67 node? Well, if you recall, the left subtree is just all the nodes that are included beginning with the root node of the subtree. So if we say the left subtree of the 67 node, well, that's just the 56 node totally by itself. What's the right subtree of the 67? It's just that 76 node all by itself. What's the depth of 56 and 76? They're both depth 0 if we're talking about relative depths per their subtrees. That means what is the height of the left subtree and the right subtree? They're just 1 because the depth is 0, the maximum depth is 0. And if we want to get to the deepest node in one of those subtrees, we're just going to end up touching the one node that's in the subtree at all. So that means I don't want to write down left subtree height right now. So left subtree height of 67 is 1. Right subtree height of 67 is also 1. So we can do this with any node we want. What is the situation with the 33 node? Let's do the 33 node. Yeah. It has a left subtree height of 2, and you can tell because, well, the left subtree starts with the left child, and the left child is going to be the root node of its own subtree. Notice how the maximum depth we can find here is 1, right? Like if we start at depth 0 for the 12, considering like it's a relative depth, then that means we take the deepest node, which is the 19 node, which has a depth of 1. We add 1 to that, so that means the height of that subtree is 2. Or if you wanted to find the deepest node in that whole subtree, how many nodes would you have to touch to get there? We'd have to touch the 12 and then touch the 19. We touch 2 nodes, so the height of that subtree is 2. Maybe I'll just put h equals 2 here. So now for the right subtree of the 33 node, it's kind of easier. We just basically only have, one node to really look at. So the right subtree is just that 39 node. That means that 39 has a depth of 0, and the right subtree has a height of 1. Whoops, height equals 1. I didn't put two equal signs. I like to do the comparison operator. We could also do the same thing with the 42 node, right? We can say, let's get rid of all this stuff real fast. We can do the 42, its left subtree starts with that 33 node. So I'm just going to highlight that real fast. The 42 node's left subtree has a height of 1, 2, 3, and you can tell because the 33 has a depth of 0, a relative depth of 0, and the 12 and the 39 have 1, and the 19 has 2. So the deepest node has a depth of 2. So that means the height of that subtree is 3. So I'm just going to do this real fast. Height is 3. And then the right subtree of the 42 node, the root node of the entire tree, is going to be this. So the root node has a depth of 0. Depth of 0. And then these other leaves over here have depths of 1s, which means the height of this subtree is going to be 2, or the deepest node plus 1, or the number of nodes you need to touch to find the deepest node. And 56 and 76, those are both equally the deepest node in those trees. Okay, so we talked about a bunch of terminology here. Let me just double check my notes in case I forgot to tell you anything. I think I'm all right. Well, maybe I should real fast just briefly mention that these nodes, I mean, this is not really part of the video exactly, but let me just mention that these nodes are objects, right, in your code. So they would have, whoops, that's dumb. Let me do a blue circle. They would have, there's like some sort of an object, you would call it a node, and then they would have pointers. They would have, each of these nodes would have a pointer to its parent, and it would have a left child pointer that goes down into the left, and a right child pointer that goes down to the right, and also a little slot in that object for the data. So I'm just going to put T-type data. In C++, I usually say that the templated data type for a node or data structure is just the T-type. That just means you could put anything you want. Like you could have your nodes hold integers, letters, strings, custom objects, whatever you want to do. And we'll talk about this more in future videos, but long story short, I want you to just imagine that every node actually has 3 pointers inside of it pointing to something else, to other nodes, rather than thinking of it like a graph, because in a graph you could have like a whole bunch of different connections, and that's usually managed by the actual graph object itself. So anyway, we're done with terminology. I hope you learned a little bit of stuff and had a little bit of fun. Thanks for watching this video. Tell your friends. Eat a donut and a chocolate, and then be really happy and stuff. Okay, I gotta go. I'm going too far. See you at a later date and time. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos, or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. Sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video, and it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? Just send me a comment. Whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all.